Thank you. Good afternoon, everyone. Okay, so in this talk, we discuss this result based on the joint work with Fernando Geronimo. So maybe let me start from some background. So we know that quantum entanglement is a distinctive feature of quantum phenomenon, and it's very important to resource in quantum information, quantum computation, quantum crypto, and etc. So for example, we know that entanglement is necessary for quantum speedup because little entanglement can be simulated by classical computation. And also we probably all know these classical results of quantum key distribution, quantum teleportation, all these early developments. They all rely on entangled states crucially. And yet the implications and limitations of quantum entanglement is not fully understood. So in this talk, we want to understand entanglement via the lens of computational complexity. Okay, so by what I mean, here we have our favorite quantum Merlin-Arthur system. So our King-Arthur, he has to face a lot of problems every day. And today, he maybe has a graph, and he wants to know whether this graph is recolorable or not. So he turned to Merlin, the all-powerful prover, for help. Merlin should send Arthur a polynomial-sized proof. And the thing is, Arthur does not completely believe Merlin. So he will do some quantum polynomial time verification on the proof. And what we want is that in the yes case, so if there exists a valid coloring on this graph, then faithful Merlin should be able to convince Arthur with good probability, say with probability at least B. And in the no case, so when the graph has no valid recoloring, then no bad Merlin should be able to fool Arthur with high probability. So say with probability S. So CNS for completeness and soundness. And we want the difference between CNS to be large, to be a constant. So we will call this completeness soundness gap. Okay, so that's standard. And now let's introduce entanglement, or I should say, let us introduce non-entanglement. So we were asked for the second Merlin, and the first and second Merlin should share no entanglement. So now Arthur can ask for each of the Merlins to send their own proofs. The requirement would be similar. In the yes case, Merlins can convince Arthur with high probability. In the no case, no bad Merlin can fool Arthur with high probability. Again, we would want this gap to be a constant. Okay, so a very natural question is just what is the complexity power of two Merlins, 2MA2 for two Merlins? And this complexity class was first introduced by Kobayashi, Matsumoto, and Yamakami about 20 years ago. Let's just maybe pause for a second. Okay, and I guess it's very clear that QMA is contained in QMA2, just because Arthur can simply ignore one of the Merlin. And congratulations, ladies and gentlemen, you have caught up 20 years development on the lower bound side for QMA2. That is the state of art, lower bound. Okay, even though it's completely possible that QMA equals to QMA2, but there are some evidence showing that maybe QMA2 is more powerful than QMA. For example, Bilal and Tapp, they designed a QMA2 protocol to certify NP-complete problems using only logarithmic size proof. The catch is that the completeness on the gap is very bad. It's 1 over poly n. So maybe it's worth to mention that you can think that if you have the full QMA2 protocol, meaning that you can use polynomial size proof, then it's not too hard to imagine that now you can certify non-deterministic exponential time complete problem. But now the gap would be exponentially small. Okay, that's one example. And the second example is that Aronson, Becci, Draco, Fesselman, and Shore, and later developed by Harold Montanaro, together they show that if you have QMA2 particle, you can certify an NP complete problem with constant gaps using sublinear size proof. So all these results are, we don't know how to obtain using a single verifier, using a single proof. So that's why we think maybe QMA2 is more powerful than QMA. But also, these results are not enough to separate QMA from QMA2. Just because we actually want both very good gaps and super short proof size. So in one of these examples, it has full gaps. In the other, the proof length is still too long. Okay, so maybe now let's turn to the upper bound side of QMA2. I think we can probably agree that the non-deterministic exponential time next is the upper bound for QMA2, simply because you can just non-deterministically guess a exponential size classical description of the correct proofs for QMA2. And then you can just simulate the DQP verifier in exponential time. Okay, congratulations again, ladies and gentlemen. Now you've caught up 20 years development on the upper bound side for QMA2. So this is a state-of-the-art upper bound, resisting like all the following attacks, like including STP, semi-definite programming-based algorithms, or using some clever epsilon net to capture the geometry properties of quantum states, or using quantum information theoretical tools like definity type theorem, or using perturbation theory. So all these attacks failed to get anything better. Okay. So maybe there is one more natural question you can ask, because it seems like two Merlins may be more powerful than one Merlin. What about three Merlins or four Merlins? Is it possible that they also have some, at least similarly powerful power? So for this question, we actually have an answer, and the answer is no. So more than two Merlins wouldn't gain you much. And this is basically due to the following product test developed by physicists. And the goal of product test is to test if a given pure state is a product state, like this form. And what the product test actually does is the following. So it will actually take two copies of the state you want to test, and then apply swap test on the first subsystem of the two copies, and then apply swap test to the second subsystem of the two copies, and so on. So think about the yes case. So if psi is actually a product state, then the first swap test is just applying to two pure equal states, so you will accept. And similarly for the other product test, so you will accept. And if psi is not product test, so it is not product state, so on some cut, there will be entanglement. So you will hope that the swap test should be able to detect the entanglement there. And the full analysis was first given by Aaron and Montanaro. What they prove is following. So given any pure state psi, if it's epsilon far away from any product state, then the product test will reject with probability in the order of epsilon. And using the product test, you can show that you can reduce the number of provers to just two. How? Well, we were just asked the two provers to simulate two k provers. So each Merlin should send what originally k Merlin should send. If the Merlin actually sends us k unentangled proofs, then we can just use the original verification for QMA K. And on the other hand, if Merlin wants to cheat by sending entangled proofs, then we should be able to detect that using product test. Okay, so that's it. So we know that QMA2 is difficult to understand, and that's why in this talk, in this work, we will restrict the system a little bit further by asking for only non-negative amplitude proofs. And that's the title. So we want to design global protocols with constant gap for these problems from theoretic computer science, small set expansion, unit games problem, constraint satisfaction problem. So in the end, we want to show that if we have this new assumption, then we will be able to capture any non-deterministic exponential time problem. So of course, we rely on our non-negativity assumption, and also we will use some properties of expansion abundance of the underlying problem. So one more thing I want to mention is by global protocol, I mean, which I didn't explain, that for Bilarian tap protocol or for Ronson protocol, in some vague sense, they treat their quantum state as classical things. So they didn't try to take full advantage of quantum state. So by global, I mean we want to take advantage of that. We will apply we'll apply unitary transformation on those states. Okay. So due to the time constraints, let's just focus on the small set expansion problem in this talk. And I hope that it will illustrate our main ideas of this result. So just to make sure we are on the same page. So by restricting proofs, I mean, regardless of the yes case or no case, the Merlin should always send proofs where the amplitude of the quantum states are non-negative. So even the bad Merlin should do this. Okay. Okay. So in this new model, there's one thing I want to mention, that the product test still works. The reason is just because the closest product state to any non-negative amplitude state is a product of non-negative amplitude states. Well, this is relatively easy to show, but let's just take it as a fact. So the advantage is now we don't need to just work with two Merlins. We can assume we have as many Merlins as we want. And this is also a partial way to get gap amplification for this new model. Of course, it will suffer the soundness of the product test itself. Okay. Now let me tell you the problem, the small set expansion problem. Here you will have a irregular graph, and you want to distinguish two cases. In the yes case, there is a small set that is non-expanding. Okay. By small set, I mean the size of this set is maybe say 10%, at most 10% of the total number of vertices. And by non-expanding, I mean whenever you look at a net, maybe a random net that touches one vertex in S, then it should stay within S. Or just look at this cut between S and S complement. So there is very few edges that can cut across S and S complement. That's what I mean by non-expanding. And then in the no case, so the opposite. For all the small sets, they are expanding. That is, for almost all the edges that touches one side in S, then it will actually exit S. So it will go across this S as complement cut. Or think about random graphs. So for random graphs, when you take one vertex inside S and you like choose a random neighbor for this vertex V with high probability, this edge is going to exit S just because the size of S is small. So in other words, the yes case is actually a small set that's showing your graph does not look random. Okay, so that's the problem. You want to distinguish the not very random case and versus the random looking graph. Okay, and now in the practical, what author would ask Merlin to send is just a uniform superposition of a non-expanding set. Okay, we will assume there we also received many equal copies of such groups. And then author will just use the fact that, a deregular graph, when you write down its adjacency matrix, AG, then you can always decompose it into like the permutations. So here is a two regular graph, 5-star, and it decomposes into a clockwise permutation and anti-clockwise permutation. And permutations are unitary operations. So author just takes a random permutation from this decomposition and apply it to the proof it received. So what do we expect in the yes case when S is a non-expanding set? Then we know that all the edges are essentially contained within S. So this permutation restricted to this set S is just a permutation within S itself. So after we apply this permutation, we obtain approximately the same state effect. In the no case, on the other hand, all the vertices inside S after the permutation are stand outside of S. Therefore, you obtain a state which is kind of orthogonal to the original state. Now, using swap test, you can distinguish these two cases. There are, of course, many ways Merlin can cheat. Among all these things, like the real threat is that Merlin can actually just send a uniform superposition of all the vertices. And by definition, all the vertices is non-expanding. So we have to deal with this. And we will discuss this in the next slide by the so-called sparsity test. Okay, but this is the complete description of the particle. And maybe besides the sparsity test part, everything here is just swap test, basically. So it's not hard to believe it can achieve constant gap. So this just shows that small set expansion problem can be solved in our model QMA +2 model using logarithmic size proofs with constant gap. Okay, so now let's take a look at the sparsity test. So at this moment, we haven't seen anything about non-negative amplitude. So here will be the actual place where we use the non-negative amplitude assumption. And recall that the goal of sparsity test is to help author to make sure that Merlin is not sending a uniform superposition of a large set. So what sparsity test will do is to prepare a uniform superposition first of all the vertices, and then ask Merlin, in addition to the uniform superposition over the supposedly small set, also the uniform superposition over the vertices not contained in S. So we will have many copies of these three states. And now we will just estimate their pairwise correlation. Because we have many copies of these states, so we can estimate to a very good precision. And what do we expect now? We expect psi and psi complement, because they are on disjoint support, they are orthogonal. So this correlation should just be 0. And then because um, we want psi and psi complement to include all the vertices, so if you do the correlation between psi and the uniform superposition over all the vertices mu, you take it squared, but the correlation between mu and psi complement squared, it will be 1. That's what you expect in a good case. And now I just claim, if you, in any case, if that's what you observe, then this correlation between psi and mu will tell you the sparsity of the support S. This is easy just because everything here is non-negative amplitude. So when psi and psi complements actually are orthogonal, it has to be the case their supports are disjoint. And then if their correlations with the mu state squared sum up to be 1, they saturate. They must saturate Cauchy-Schwarz inequality. It just means psi should be a uniform superposition on support. Yeah. So once we know it's a uniform superposition over S, then we can by just looking at the correlation between psi and mu, we know that its size. So that's it. Okay. So to actually go from the small set expansion particles to the full particle, maybe for the non-deterministic exponential time problem, you need some more tools from theoretical computer science. For example, what we are actually facing is an exponentially large constraint satisfaction problem. And this constraint satisfaction problem where comes from an NEXP complete problem, and we were, give it some structure based on probabilistic checkable proofs and expanded graphs. And the main challenge here is that everything here is exponential size, but your verifier is only BQP time. So there is some mismatch, and you need to add some more structure to this case DSP, such that even BQP verifier can handle these things. Okay. Okay. So basically, that concludes what I want to say about QMA plus 2 equals to NEXP. Of course, the natural question you probably were asked is, what about the QMA, the original QMA2? Well, at least I can say that QMA2 and QMA plus 2 can simulate each other to some extent. Maybe you have already seen it in the previous talk. So the first direction is kind of trivial at this point. QMA2 is definitely containing QMA plus 2. The other direction, QMA plus 2, is also containing QMA2, but you have to lose some soundness. As a corollary, you can just say, okay, if we can design QMA plus 2 particle for an XP problem with a really, really good completeness soundness gap, then you can show next is containing QMA2. So now you don't want an arbitrary constant gap. You want really good gap. Like here, I say point larger than 3/4. So the problem now goes to the gap implication for QMA2. And as I mentioned, product test works for QMA plus 2. So I think at least that's something you can do some gap implication for QMA plus 2. Okay, that's of course not enough to get good enough to get the really large gap implication. Okay, so that's I think all I want to say. Thank you for listening.
All right, thank you, Pei, for the great talk. We have time for maybe 1 or 2 questions. I have a quick question. So what's your current belief about QMA2 plus versus QMA2?
I don't know. I don't know. But yeah, I don't know. I hope it equal to AXP. I think that's a more interesting possibility. Yeah.
That'd be pretty cool. Other questions? Okay, if not, let's thank Pei again. Thank you so much.
Thank you.